Okay, let's go through the Newton's second law review. This is a pretty good review for the quarterly exam, at least for the 60% or so of the exam that pertains to forces. Um, doesn't mean that everything that's on the quarterly is going to be here, but the concepts certainly are. So the first one here, we're looking at a graph of force and time. We are going to do more with force time graphs later on. Looking at the area under the curve, for example, will tell us a little bit more about the motion of the cart, or the block in this case. But this is pretty straightforward. It just says if we imagine what this block might look like, right, we can think about a block that has a force applied F. It says it's frictionless, so we could assume that F is the net force. So that means that F equals mass times acceleration. What we're given here is a varying force, but it does say that at 3 seconds here, the acceleration is 5. So we need to look at the graph to see, well, we know that at 3 seconds we have 15 newtons of force applied. So the mass must equal 15 newtons of force over 5 meters per second squared. A newton over a meter per second squared is equal to kilograms. So that means we must have a mass of 3 kilograms. Okay, the second one we did, I don't know if everyone, but we did something very similar to this one in class. So this should be a good little review. Remember, two objects always means two equations. Do not, I repeat, do not try to come up with shortcuts for these. We want to derive the expressions every single time. Trust me on that. The practice is good for you, plus the total number of possible types of force problems is too great for you to try to memorize all those shortcuts versus doing it one way, the right way, every time. So we always start out with two diagrams, right? So if I have two objects, I need two diagrams. We're going to make that the 2 kilogram cart, make that the 1 kilogram or block again. So we look at the diagrams. I'm not going to worry about the vertical forces here because it's a flat surface. So I know that, the normal force and the weight of each block are just going to simply cancel each other out. And that's not really going to do anything for me solving the problem, which is really all about the horizontal motion and forces. So on the first block, I'm going to say, okay, I'm told that I have a force F acting to the right. Well, I also have a string in the middle, and there's a force of tension in that string that, remember, you cannot push a string. So that tension is the same everywhere in the string, but it's always pulls. So I have tension pulling to the left on the 2 kilogram block, but then I have tension, the same tension pulling to the right on the 1 kilogram block, which, and then again, there's no friction. So the only force on the 1 kilogram block is just that force of tension. So now I can, the next important step here is to simply translate these, right? Sum of the forces has to equal MA for both. And again, I haven't really even read the question yet. I know I need to break this thing down and get it into simple mathematical form. Then I'll look at the question and figure out what I'm supposed to do. But sum of forces, so that means for the first block, T has to equal 1A. I leave the units out. I know it's not a great practice, but it helps you see through to the simple algebra of it. And then on this one, I'm just translating. F minus T has to equal 2A. Okay, so now I have two simple expressions. And I'll now look, let's read the question. When the frictionless system shown above is accelerated by applied force of magnitude F, I think we're missing a letter there, the tension is what? All right, so I want to look at what is the force of tension in the string when I pull on this with some force F. Okay, so first of all, we have two common variables. Again, it's one system connected by a string. So it's one system, meaning it has one acceleration, and it's one string, meaning it's one single tension. So same T, same A, but acting on each block individually gives us two separate equations for each block. So if T equals 1A, what I don't really want in my equation here is A, because it's saying the tension is, right? So I want A to go away. So if T equals 1A, then A has to equal T over 1 kilogram, or A equals T. So I can plug that in over here, and I could say, okay, that means A equals T, so F minus T equals 2T. Okay, now we can solve. F equals 3T, or the way they want it, T equals F over 3, right? So T equals F over 3, 1/3 F. That makes sense, right? Take a look at what we're saying. Newton's second law says acceleration equals sum of the forces over the mass, right? That's a version I like more than F equals ma. So if F, think about if these two blocks were not connected by a string, but what if it was just one big block of 3 kilograms? F is accelerating 3 total kilograms of mass. Excuse me. So the string is only accelerating 1 kilogram of mass. So 3 times the mass means F has to be 3 times the value of T, which, solving this for two equations, gives me exactly that. And that's a strategy, or I wouldn't even call it a strategy, it's just how you do it. Two objects, two diagrams, two equations, and then we solve those two equations for however we need to. In this case, we were looking for T. Maybe the question was find A or find F, but either way, we're never going to change the way we start these problems. Okay, same problem, but instead of having now a tension between two objects, we're simply going to have two objects directly pushing on one another. This, for whatever reason, is a very common AP Physics 1 type of problem. Again, you don't want to get wrapped up into trying to combine this and find some kind of a shortcut for it. Just do two diagrams, and don't try to do it on the same one, because that makes it confusing when they're touching in the picture. 3 and 2. Remember, the only force in this situation that can act on either one of these boxes without actually touching them is the force of the Earth's gravity, which acts through a field. And that doesn't even play a part in this problem. Again, this is a horizontal problem, so we don't have to worry about the vertical forces of gravity and normal force here. They don't contribute to this problem. So let's think about it. I have some applied force here. It says it's 20 newtons. And I also have the force. I'm going to just label those as the 3 and the 2. Maybe I move the 2 over a little bit. So I also have a force from block 2, right? So the force of block 2 right here pushing this way, and then the force of block 1 is pushing that way. And actually, we could refer that to Newton's third law, that if block 2 is pushing on block 1, it's actually the same as saying tension, right? One string has one tension. Well, block 3 and block 2 are pushing against each other. That's the interaction nature of force. 3 acting on 2, 2 acting back on 3. So block 2 then only has one force acting on it, and that's just the force of block. I'm calling it 3 because it has a 3 kilogram mass. That's just how I'm labeling it. And there we go. So now let's translate to an equation. So sum of the forces equal mass times acceleration. Sum of the forces equal mass times acceleration. Drag and drop. 20 newtons minus the force from block 2 has to equal 3A, right? 3A, 3 kilograms. Over here, force acting from block 3 has to equal 2a. You notice this looks a lot like the last problem with the tension because it is exactly the same problem. Tension, there just happened to be a rope connecting the two blocks. In this case, it's just the two blocks pushing directly on one another. So two blocks are pushed. Now I can read it and solve it. Two blocks are pushed along the surface by a force of 20 newtons to the right. The force that the 3 kilogram block exerts on the 2 kilogram block, 3 kilogram block exerts on the 2 kilogram block. But let's make this very clear. The F force of the 3 on the 2 is the same as the force of the 2 on the 3, right? And that's Newton's third law. But we also can just simply, we don't need to spend a day on Newton's third law to appreciate that that's the same as saying that there's only one force of tension in a rope. They are both pushing against each other with the same force. So I can just call that F, right? I don't even need these subscripts because it's the same force. So if we're solving for that, then we can say that we need to get rid of that A. So A equals F over 2. So let's plug that right in over here. I'm running out of space here. So 20 minus F equals 3 times the quantity F over 2. I just substituted F over 2. So I get 20 minus F equals 3F over 2, or 1.5 F. So that means 20 has to equal 1.5 plus 1 equals 2.5 F. So F equals 20 over 2.5. What's that? 20 over 2.5 is about 8, right? So 8 newtons to the right. Let's see if that makes sense again too, right? So if 20 newtons pushes 5, right? So acceleration equals force over mass. So 20 over 5 has to equal, right? And then the force on the 2 has to equal F over 2. So I get the same thing, right? 40 over 5 equals 8. So 8 newtons to the right.